Hello, this is the presentation that I presented at Page in Budapest in June 2017. I think the title, The 6 Biggest Pharmacometric Modelling Mistakes, needs a little clarification. The first thing is that this is about the technical aspects of modelling and simulation. It's not about other things, so modelling in a model-based drug development program or communication of models to clinical teams. I think the second thing to mention is this isn't perhaps the 6 biggest pharmacometric modelling mistakes, but rather I've taken examples across the spectrum of modelling activities, from design through to model predictions. My goal today is to help you avoid some of the mistakes that I've made or seen over the 20 years that I've been doing modelling and simulation. How I model today is rather different to how I was taught, and I would like to share with you some of those observations. My second goal today is to ask you to challenge your own modelling toolkit. So our model building strategies and the methods and what we use when we develop our models, to look at those critically. I think we're all indebted to our educators, both past and present. I very much like this quote from Isaac Newton: "If I've seen further than others, it's by standing upon the shoulders of giants." I wouldn't claim to have seen further, but I've clearly stood on the shoulders of giants. So for example, every day we have calculus and logarithms, a key part of the modelling work that we do, but I'm not sure I would have been bright enough to have come up with them. However, I think we should not assume that everything that we were taught was faultless. So this quote by Rene Descartes: "Some years ago, I was struck by the large number of falsehoods that I accepted as true in my childhood, and by the highly doubtful nature of the whole edifice, the whole system of beliefs that I subsequently based upon them." This quote resonated with me and reflects my own path as I began to challenge and reject perhaps some of the methods I was taught when I was at college. So the advice here is, don't believe everything you were taught 100%, and I guess by extension what I say today, even though I sincerely believe it to be true. So where can errors come up? I think this is a useful overview of the modelling process. At the top here we have the design and the data space, and that's the most important. It controls the data that we're going to get. So that's the number of subjects, the number of dose levels, the number of measurements within a subject, and that's really going to be key. Why is that key? Because it controls the model space, the models that we can consider, and that conditions on that design and data space. So for example, if we're interested in doing modelling the absorption in pharmacokinetics, we really need plenty of samples in that absorption phase so that we can compare and differentiate different absorption models. And finally, there's the parameter space. So what are our best estimates of the model parameters and the uncertainty around them? They're conditional on the design that we used as well as the model selected. So the advice here is that the most important is the design, then the models, and then the parameters. So error number 1 is when a poor design limits the model space. What do I mean by that? So with a great design, we can clearly differentiate between good and bad models. So over here, we have this very beautiful sigmoidal Emax model fit to the data. We have the pharmacodynamic response here on the y-axis. We have dose on this axis. And on the right side, we have the log linear model fit, where we're trying to fit a log linear model to this data. And what it says down here is that the log linear model fit is clearly worse than the sigmoidal Emax model fit. The change in -2 log likelihood, so the change in the objective function, is 35 points. So no one would choose the log linear model fit over the sigmoidal Emax model fit. So that's with a great design. This is the same data, but only at doses 3, 10 and 30. And now on the left we have the sigmoidal Emax model fit to this limited design. This is with only the limited number of doses. And on the right we have the log linear model fit. And here we see that the log linear model fit is not clearly worse than the sigmoidal Emax model fit. The change in -2 log likelihood, the change in the objective function, is 0. So with a poor design, we may struggle to differentiate between the good model on the left and the poor model on the right. So error number 1 is when a poor design limits the model space. So we need to always consider how our design could limit the ability to fit the models we wish to consider, as well as it can limit our ability to differentiate between candidate models. So when we have the log linear model versus the sigmoidal Emacs model, we need a good design to be able to differentiate those bad models and good models. So some of the consequences when we don't have a good design, well, that's ultimately going to lead to poor inference. So that's when we're going to be forced to fit overly simplistic models, like the log linear model there, or forced to fix or guess model parameters. And that's ultimately going to lead to poor decision making. As well as that, we will potentially get biased estimates. So for example, the inter-individual variabilities and the pharmacokinetic absorption parameters, if you only have very limited data in the absorption phase. So the advice is to appreciate that fitting complex models to weak data may be a recipe for disaster. We cannot just dump our ideal model onto a weak data set and expect everything to be okay. So to resolve that, and at the design stage, assess if you'll be able to fit and differentiate between the candidate models that you're going to be interested in fitting. Error number 2 is on model selection and on the misuse of hypothesis testing. So I was taught at college the principle of parsimony, this idea of the simplest model that adequately describes. And I now look at that and I think it's poor modeling science. Simple, I think in most cases, doesn't equate to smart or sensible or sound. If you recall that log linear model fit before, that really was a simplest model that adequately describes, but it wasn't perhaps the right way to go. I think significance testing and the parsimony principle have become these two twin devils. Just because something is not statistically significant, it doesn't mean it's not important. It doesn't mean that we can just ignore it. Significance testing, it's important to understand, depends on the design, as well as the number of subjects, as well as the true effect size. We're going to go through an example around that in a moment. And I think finally on this slide, I just wanted to mention, I think we should try to avoid these weasel words like no evidence of a difference with respect to age or sex or race, for example, in a POP-PK report, basing that statement on results from non-significant results. I think it's much better if we provide the estimate and a 95% confidence interval rather than use these weasel words. So what is hypothesis testing good for? Well, hypothesis testing is really useful for identifying weak and hence not interesting models. So over here, again, we have our rather beautiful sigmoidal Emacs model fit with based on 200 patients per arm, and we're estimating the Hill coefficient down here of about 1.5 with an approximate standard error of 0.23. Over here, we're fitting a simple Emacs model fit, so therefore the Hill coefficient is fixed to 1. And the change in -2 log likelihood between this model and this model is 9.2. So it's showing that this is a better model than the simple Emacs model fit. However, we can't use non-significant differences to rule out models. So in that previous example, we had 200 patients per arm. We saw the 9.2 change in -2 log likelihood. And most people would be happy to estimate the Hill coefficient, and indeed that's the correct decision. However, if we halve the sample size or half the sample size again, we're going to have an expected change on the -2 log likelihood. The change in the objective function is going to half and half again. And if you rely on this significance testing approach on 1 degree of freedom, the critical value is 3.84. So the danger there is that you say when you have very limited information, you're going to fix the Hill to 1, which is going to be the wrong decision. So this idea, as we go down the table, our information is getting weaker and weaker, and it's clearly an error to be more sure that the Hill coefficient is exactly 1. The subsequent modeling predictions may be biased and or too narrow. And in this case, they're going to be clearly wrong because the simulation did use a value of 1.5. So the advice here is, I think hypothesis testing is great to rule out clearly worse models. However, it's not good for differentiating between similar fit models. So for those similar fit models, you should generate the predictions and see would the effect on decisions matter around that selection of the different models. Error 3 is in model assessment, and this is when people are using simple diagnostic plots as evidence a model is sound. So nonlinear mixed effects models are complex, and the ability of random effects to generate good fits, even when a model is very poor, should always be appreciated. So some simple diagnostic plots, such as DV versus IPRED, DV versus PRED, I think provide very limited evidence that a model is sound. And personally for me, I think these are kind of archaic plots that provide no evidence a model is okay, and I think we should perhaps leave them behind. Why do I say that? Well, I think it's straightforward to create examples where these plots are misleading. So here is an example. I'm going to show you the data behind these plots in a moment, but on the left we have DV versus PRED, and everything seems to look fine, and DV versus IPRED on the right, where we seem to have this kind of perfect fit type data. So the plot looks very good, but I'm going to show you that the model is a bad one. So I think the reliability of these plots and the usefulness of these plots is quite limited. So here is the data behind that longitudinal model fit. These individual fits look great. So what do we have here? We have 6 patients who received drug, 6 patients who received placebo. We have week 0, week 2, week 4, week 6, week 8. And the simulation here is using a drug effect for all the drug subjects post baseline of -1. So down here, this is about a -1 reduction across these 6 subjects. So the model appears fine, but what's the problem with this model? Well, this model is actually fitting a really stupid drug effect model. The drug effect actually depends on the ID number. So for subjects 1, 3 and 5, the drug effect is essentially 0, and for 2, 4 and 6, the drug effect is -2. So this is clearly not a good drug model. However, those original plots actually look nice. So the advice with regards to DV versus PRED, DV versus IPRED, I think you need to be careful not to overinterpret these basic plots. They are indeed very basic plots. I think the second piece of advice is to use random effects carefully. They can make a bad model look good. So what they're going to do is they're going to try to match the data as well as they can, and that has the potential to actually make a bad model look quite good. The third piece of advice is consider residual analysis by an old stats book and try DV minus IPRED on the y-axis rather than these plots. Error number 4 is visual predictive checks, and it's using simple VPCs to argue a model is sound. So predictive checks, or VPCs in the pharmacometrics world, are an excellent way to challenge a model. Although I think most VPCs I see do not really challenge the critical parts of the model, so the drug model, in any meaningful way. A nice VPC is often just a reflection of baseline inter-individual variability, and it's really that we need to use more challenging VPCs than this. So what we have here is the pharmacodynamic response, again through time. We're using the same nonsense drug model as before, where some patients were having the drug effect and some were having no drug effect, but with 100 patients and a higher baseline inter-individual variability. And the large baseline inter-individual variability here is hiding the model inadequacies. So this type of basic VPC is really not useful for challenging the model. It actually gives the impression the model is okay when we know the model is actually not okay. It's just worth quickly mentioning, a better VPC would show the model inadequacies here. So now we have change from baseline on the y-axis against the week, and because all of the patients were being simulated with a treatment effect of around -1, the observed data, which is shown in the red, is all around -1, but the model is simulating some much wider range of outcomes. So this really would show the model inadequacies with this type of VPC. I think that you can try some much more interesting VPCs. So I think it's great if you can show that your model can describe each component of the observed data. So can the model just describe the baseline first of all? Then can the model describe the baseline and the placebo? And then can the model describe the baseline and the placebo and the drug? And I think that the note up here It's just to mention that to use these during model development, don't do this right at the end to find out there's a problem, but actually build it into your model building processes. And I think just down here, just mention, you can actually have some very interesting VPCs and predictive checks. So for example, the percent of drug patients with a 50% improvement minus the percent of placebo patients with a 50% improvement by time point. And if you are really describing individuals, you'll be able to describe these features of the observed data with your model. So the advice, use VPCs to challenge every part of your model, and then look at these deltas, the change from baselines, the change between time points, the change between doses, to really challenge your model. Error number 5 is around model uncertainty, and this idea of selecting a single final model. I think historically we've tried to seek a single final model, but I actually don't think that's great science. I think this mindset needs to change. We should view model uncertainty in the same way as we see parameter uncertainty. That is that it's always there, and it's naive to pretend it doesn't exist. I think we would look very strangely on an individual who presented a model and said there is no parameter uncertainty, but strangely we would accept perhaps an individual who only showed one model, even though they actually considered over 100 models. I think the robustness of conclusions, so for example dose selection across a range of candidate models, is actually very compelling. If we find out the results across those different models, across that model space, actually change the results, well, we can actually do something. We can plan accordingly. So we can hope for the best, but actually we can plan for the worst. So if there are models that suggest a bad outcome may be possible, we can perhaps change the way we design the subsequent studies. So the advice here is, if you can't clearly distinguish between competing models, then don't. And progress all those candidate models to the prediction stage to see if the model choice is actually critical to the decision that you're going to make. Error 6 is around parameter uncertainty, and I've said provocatively here, say no to the nonparametric bootstrap. I think the nonparametric bootstrap is ubiquitous. I think we're all amazed how simple it was, how quickly we could code it. So who taught you the theory part? We wish to know the joint distribution of the model parameters, conditioning on the model and the data. So why are 1000 sets of maximum likelihood estimates from the nonparametric bootstrap equivalent to that? And I think this point goes back to the Rene Descartes statement, whereby we may initially believe something to be true because someone told us that it was a useful way to do something, but actually when you dig a little bit further down, you may look at it in a slightly more critical light. I think we could give a whole presentation on the limitations of the nonparametric bootstrap, but I'll just encourage you to think about those last two statements and why you think that there's an equivalence there. So the advice, I would say, I'm now a fully paid up Bayesian, so I'd say Bayesian Monte Carlo Markov chains are a beautiful way to describe the joint distribution of the parameters. I think if you haven't started using Bayesian analysis, I would encourage you to try it. I really don't think you'll regret it. I think I've started using Bayesian MCMC 5 years ago, and I really can't see myself going back for any final models now. As a summary, I think it's important to continually challenge our modelling toolkit. I hope this presentation was informative and has made you think. I hope the advice will be useful. If you disagree, I'm always happy to learn. Give me a call. And I'll say good luck going forward with your modelling activities. A quick thank you to Janet Wade and Katja for kindly providing comments on an early draft of these slides. Well, that doesn't mean that they endorse everything that I've said today. And thank you.